One last thing about diffraction, about this chapter, is what happens when you have a circular aperture and you send light through it. Okay, we already discussed the case of a slit, right? Just single slit, you send light, and we know that on the other side of that slit, the light is going to open up, right? There's going to be a cone where, if you remember the picture of Humboldt Bay, that's what you see there, right? The waves are spreading out past that constriction. But if it's not a slit, right? A slit is a very elongated rectangle, but if it's a circle, right? Then the equation that describes the bright fringes and the dark fringes is not so easy. It's a Bessel function, and we don't need to talk about that. But I just want to point out what the pattern that you see looks like. So you would have in the center, just as before, you would have the central maximum, which is a lot brighter than everything else. So if I were to do the demo here and project that on the column, you will be able to see the rings, but a camera would not be able to pick up the rings, because this is a lot brighter than the rings surrounding it. With your eyes you can do it, because eyes are extremely good at catching contrasting differences in contrast, or minimizing differences in contrast. But this is what you would see. So you have light expanding out of this hole in cones, right, with different opening angles. And if you are to do the usual picture that we've been doing when we talk about interference on diffraction, we look at the side view of the whole thing. This is what it will look like. You have, say, plane waves coming in from this side. They go through the circular aperture. This is now a circular aperture here, not a slit. And they come out, they expand like that. Then you have other maxima, the fringes, dark fringe right here, right? But then there is a bright fringe here. And if you look at the intensity profile, if you use the screen to be your axis and you plot in this direction the intensity profile of that light hitting the screen, you will find a profile like this. It goes up in the central maximum. I should have probably made it a lot taller here, because the central maximum is a lot brighter than the side fringes. But that's the general shape of it. And you have dark fringes at certain locations. So what you call the width of the central maximum, the width of the central maximum, in the book they call it W, will be the distance between this, between the top, this point on the dark fringe, and the bottom of the dark fringe. So the angle that describes where the dark fringe is given by this expression. This is a solution, like I said, of a Bessel function. In your homework, they show you the location, the angle for the second dark fringe and third dark fringe, and so on. The most important one to remember is fringe number 1. So that dark fringe determines, as I said, the width of the central maximum. So if the angle at which the dark fringe is given by theta 1 in that equation, then if the screen is far enough, you can say that this width is going to be 2 times L, the distance, this radius, let's say, of the circle, is going to be L times 2 times this angle. So that's where the factor of 2, 1.22 times 2 is 2.44 times L, and this is 1.22 times lambda divided by D is the angle theta 1 at which you find the first dark fringe. Okay, so that's an expression to tell you the width of the central maximum. Notice how that expression depends on the diameter of the pinhole. This is very counterintuitive. If you make the pinhole smaller, D smaller, the central maximum grows. You send in light, you drill a tiny little hole in your sheet of paper. What the bright spot on the other side looks like is a circle that is growing as you make the holes be smaller and smaller. Okay, so the more you constrain the wave to go through a very narrow passage, the more it's going to or expand on the other side. This behavior of light is very important in astronomy, because if you have a telescope pointed at a faraway star, which looks like a point, right? You know that when you get the image of that star on your film or whatever you're using, when you project that image, it cannot possibly be a point. It's going to have a shape, a circle, a finite width on the film, right? Because when the light approaches the telescope, the only light that you're going to receive, that you're going to record, is the light that manages to squeeze through the telescope, right? The telescope has an aperture, it's usually a circle, right? So the light is coming in through that circle, and because of that, then there's going to be that point particle, which is generating plane waves. Those plane waves, when they hit the opening of the telescope, they're going to have this behavior of opening up, and the image of the star will not be a dot, it will be a circle, and there will be fringes around it. So that's important, because if you have two stars that are really close together, since each star generates an image that has a finite width, then those spots, the central maximum for the light of each star, they can start to overlap if the stars are too close together. They will start to overlap, and at some point you won't be able to tell the difference between one star and the other. It will just look like one bright spot, even though there's two stars there, right? So Rayleigh's criteria, and we're going to talk about this some more when in the chapter of optical instruments. Rayleigh's criteria tells you that the minimum angle between, so if I look at a star over there, my arm makes an angle of something. If I look at the star next to it, my angle has to move a little bit, and the angle is different. That difference in angle is called the angular resolution. How small can that be before you can distinguish that the two stars are different? The angular resolution, the minimum angle that two objects can have in the sky, so that you can tell them apart, is equal to this theta 1 in our equation for circular aperture, which is the 1.22 times lambda divided by d. That's the minimum angular distance between two objects. So that's called the angular resolution of a telescope. If two points have a bigger angular distance between them than this, then you can tell them apart. If they're closer than that number, you cannot tell them apart. And the same, I'm talking about a telescope, and you might think that that's not important for you, but for a human eye, for example, it's the same story. Right? It's an optical device, it has an aperture, which is your pupil, and when you're looking at a very tiny object far away, the image of that tiny object on your retina is not going to be a point, because light has to squeeze through the pupil. So it expands after the pupil, and it makes it would have an image with a finite width W given by the equation that we just talked about. So you can have perfect eyesight, and when you're looking at the chart in the eye doctor's office, there will be a size of the letters beyond which no human could possibly resolve it. Just because the size of our pupils is a certain number, it can be very dilated, but it's not going to be more than, say, I don't know, 5 millimeters or something like that. That will determine the resolution of your eyes. It's a physical limitation that cannot be broken.